Hi, everyone, and welcome to another Flan Talk. Today we have Dan Friedman here from Princeton, where he is a PhD student. And today he's going to talk to us about representing rule-based chatbots with transformers. You can take it from here, Dan.
Okay, yeah, hi everyone, and thank you for having me. So this is a project is a joint work with Abhishek Panigrahi and Danshi Chen, who are also at Princeton. Um, and Feel free to interrupt at any moment. This would be a sort of more of a casual talk. Um, yeah, so happy to take any questions at any point. Okay, so this project is an example of what we can think of as a bottom-up approach to understanding transformers. So for a particular task, can we try to like explicitly construct, set the weights of a neural network that could solve that task? Um, I think there's like a few distinct reasons why this sort of bottom-up approach um, can be interesting. So one is as a way of characterizing the expressivity of neural networks, kind of in a formal way. But I think this sort of bottom-up approach can also be useful for interpretability. So if we want to understand real neural networks, having some sort of like abstractions or general ideas of patterns that these models can do, this maybe could be helpful for guiding us in kind of knowing what to look for. Um, and Having these kind of bottom-up constructions can also help us predict where a particular architecture might struggle. So maybe we can predict what tasks will be easier or more difficult to learn. There's a lot of prior work in this kind of category, including a lot of great work by people in this Zoom. So there's been a number of papers on um, constructing transformers to recognize different kinds of formal languages, so largely for characterizing expressiveness. Um, there have also been constructions of simple kind of probabilistic language models. So like how could a transformer represent a topic model, for example, or a PCFT or an n-gram model. There have been transformer constructions for what you can think of sort of as an algorithmic kind of task, like sorting or counting. Um, and also some interesting work on using explicit transformer constructions to make predictions about where transformer might struggle to learn or struggle to generalize. Um, in this work, we wanted to know, what about, like, could we kind of extend this sort of bottom-up approach to understanding a conversational setting? So um, most of these prior works are addressing different kinds of synthetic or really sort of single sentence tasks. But nowadays, our most popular transformers are chatbots that we have conversations with. And so we wanted to explore, how could a transformer carry out a conversation? Um, and our idea is like we can use some old school rule-based chatbots as a setting for thinking about some of these questions in a simplified and controllable manner. And in particular, we decided to try to figure out could a transformer implement the classic ELIZA chatbot algorithm. So ELIZA is one of the first uh, chatbots in computer science from Joseph Weizenbaum in 1965. Um, and The ELIZA, it's simple, but actually it exhibits a number of kind of sophisticated behaviors, uh, which I'll get into in the next slide. And it's also interesting because there's a number of connections, as we'll see, to recent work on transformer constructions, in particular trying to connect transformers to algebraic automata. And so we'll show ELIZA gives us sort of a setting where we could try to build on and extend some constructions from prior work to try to like give rise to something a little bit more that looks a little bit more like a chatbot, like a conversational agent. Um, and so in the first part of the talk, I'll talk about uh, construction for a transformer that can implement this ELIZA algorithm. Um, so this is in part building on prior work, and especially by trying to recast the ELIZA algorithm in terms of finite state machines. Um, but We'll also highlight cases where we can identify multiple plausible ways that a transformer could solve some component of the program. Then in the next part of the talk, we did a bunch of experiments where we trained transformers from scratch on ELIZA transcripts and tried to understand what about the task is maybe easier or harder for these models to learn, and also to what extent do the learned models match our different constructions. So especially when we have these multiple options. Okay, so to start off, here's a little background on the ELIZA algorithm. So here on the left is a example of a transcript from Weizenbaum's original ELIZA program, which I've adapted a little bit. So the gray bubbles are the user, and the blue bubbles are the model's response. And we can conceptually break down ELIZA into three parts. So kind of the bulk of the program is what I'd call local pattern matching. So an instance of ELIZA is configured with an inventory of decomposition templates associated with reassembly rules. So a decomposition template is essentially a simple regular expression for matching, for comparing the user's input to some kind of pattern. So in this case, in the ELIZA template language, the zero symbol is a wildcard. So this could match zero or more of any kind of word. And so this example template will match an input that starts with the word my, then has any number of words. It has the word me in there sometimes, and any number of additional words. So this template will match an input like my boyfriend made me come here. The decomposition templates implicitly decompose the input based on the wildcards. So in this case, if we compare the decomposition template to the different parts of the input, we can break down this particular input into four groups. So we have the first word my matches this first symbol of the template, then boyfriend made matches the second symbol, which is this wildcard, then me and come here. And for every decomposition template, ELIZA has one or more reassembly rules, which explain how to respond to that to an input that matches that template, possibly by copying some parts of the user's input. So in the reassembly rule, there will be words and integers, and the numbers refer to different segments of the decomposition template. So in this case, the 2 in the reassembly rule refers to the second group in the decomposed input. So in this case, boyfriend made. And if you fill in the second group for the 2 and the fourth group for the 4, you get ELIZA's response. Your boyfriend made you come here, ? So that's kind of like the most, maybe the bulk of ELIZA's behavior. We think of as these local template reassembly rules. But ELIZA also has two kind of tricks for incorporating some of the long-term context of the dialogue. So this gives rise to the appearance of maybe more sophisticated memory. The first example is a mechanism for cycling through reassembly rules. So every decomposition template can be associated with a list of responses. So in this case, we have this decomposition template. I'm sad, unhappy, or depressed. And it's associated with 2 different responses. And the rule in ELIZA is every time, if you match a decomposition template more than one time, then you should cycle through the list of responses to avoid repeating the same response too many times in a row. So in this case, the first match, if he thinks I'm depressed, ELIZA will respond with the first response. I'm sorry to hear you're depressed. And then the next time the user's input matches that decomposition template, ELIZA will move on to the second response. Can you explain what made you unhappy in this case? So this is like one simple way that the ELIZA's behavior depends on the full conversation history, not just the previous turn. The other memory mechanism is called a memory queue. So if the input contains a special keyword, which by default is the word my, then ELIZA will add it to the memory queue. And later in the conversation, if we have an input that doesn't match any of the templates, ELIZA will read the first memory from the queue. So in this example, uh, the first input, my boyfriend made me come here, that matches the keyword, so ELIZA will put it into the memory queue. And then later in the conversation, ELIZA sees a word that it doesn't recognize, so this doesn't match any of the templates. ELIZA will read this memory from the queue and say, does that have anything to do with the fact that your boyfriend made you come here? So these tricks are all pretty simple, but together they can kind of give rise to like the appearance of more kind of sophisticated conversational behavior. Um, one kind of side note is that we can distinguish between the ELIZA algorithm, which here I have illustrated on the left, and the particular set of pattern and transformation rules, which in ELIZA are called the script. So the generic ELIZA algorithm is this kind of abstract procedure for comparing the input to a set of templates and reassembly rules, and then transforming the input according to the highest matching rule. But then we can get different kinds of ELIZA by plugging in different sets of the actual rule, the templates and the reassembly rules. And a side question which we have not explored in the paper is it's sort of interesting to think about, like to what extent could a ELIZA model trained on one script generalize or adapt to another script, and sort of in general, to what extent can we distinguish the algorithm from the configuration when we translate ELIZA into a transformer? Okay, so that's kind of my overview of ELIZA, and here's like a schematic illustration of our transformer outline. So in this paper, we're considering a decoder only, like autoregressive transformer, and so the input at every step will be the concatenation of the entire conversation transcript that we've seen so far. And just at a very high level, we need to start off by segmenting the input. So dividing the transcript into turns and responses. Then we'll match the inputs to our set of decomposition templates in our configuration script. So in this case, we have to match all of the templates kind of in parallel to see which of our possible options matches the input. Then once we've found the matching templates, we need to select our response rule. So this could be a simple, local responses to the previous input, or it could involve either of these two memory mechanisms. So cycling through the responses or using the memory queue. And then finally, we have to generate a response, possibly copying the previous input, or maybe an input from a lot earlier in the conversation, in the case of this memory queue. Okay, so I'll start off with our approach to matching templates. So that's this first part of ELIZA. So the problem is, given an input sentence and let's say a particular decomposition template, we need to do essentially two things. So first, we need to determine if the input matches the template. So in this case, we just want to know, does this particular decomposition template match the input? But also, if it does, we also want to decompose the input according to that template's decomposition groups. So we want to divide the input into these numbered segments so that we'll be able to refer to them in the next step when we need to copy different segments according to the reassembly rule. I won't go into great detail about this part of the construction, but the main idea is that the ELIZA templates are essentially regular expressions without any stars. So we can recognize these by simulating a corresponding finite state automaton, building on constructions from existing work. So at a very high level, if we have a decomposition template that has, say, 4 symbols, so 1, 2, 3, 4, at every layer in the transformer, we can check if the first L symbols of the reassembly rule have been matched at each position. So here's like a very kind of sort of hand wavy illustration of what this would look like. So here, every layer or every row in this table represents another transformer layer. And so the idea is that at each layer, we can use an attention head to check if the decomposition template up to that layer has been matched at this point. So maybe at the first layer, we can see that at all of these positions, the word my has appeared on the left. So we've already, matched the template prefix my 0. And we can use a feed forward layer to kind of look at the previous template match in the current word to see if we can kind of proceed to the next symbol in the decomposition template. And then, so in this case, we can see that at this position, we have my 0 and then the word me. And then the next layer can kind of repeat this process with the next longer segment of prefix of the template. Until at the end, we can kind of look at all of the templates or template prefixes we've matched so far and kind of calculate based on that what symbol what's the longest prefix of the template that we've matched at each point. So we can use this to kind of reconstruct these different numbered groups. Yeah, there's more details in the paper, but this is just kind of a very high level illustration of what we can do. And some kind of details are first, we want to recognize, or we want to match all of the templates at once. So in ELIZA, we have, some whole inventory of templates, and in parallel, we can check, has the transformer matched each one of these templates individually? So then at the end, we can decide what's the best template for this particular input. And our construction just uses 2 generic fixed attention heads per layer, one that attends uniformly to the full prefix and one that just attends to the previous position. And so like very kind of high level scaling notes are in this construction, the depth of the transformer is scaling linearly with the length of the longest template in our configuration. And the width scales with the total number of templates because we need to match all the templates in parallel and store for each template some information about the longest matching prefix at each layer. So the next thing we have to do is generate the response. So assume we've decomposed the input and we've picked a reassembly rule. How can we actually carry out this reassembly rule to generate a response? And so at each generation step, we need to do a few things. So one is to calculate what we call the reassembly state. So which symbol of the reassembly rule are we processing at each step? So by that, I mean, are we at the first step, we just need to generate the word your, or are we in this second step, so we're doing the copying, right? So if the state is a constant word, then it's very easy. So we just have to generate, that word from the reassembly rule. But if we're processing a number, then we need to copy the next token from the corresponding decomposition group. To identify the reassembly state, one way to do this is just by counting basically the number of tokens we've generated so far, along with the number of tokens in each decomposition group. So here's another kind of toy illustration where we've assumed we've already decomposed the input into these numbered groups. at each step, if we just count how many tokens have we generated so far, and also how many tokens are in each one of the decomposition groups, we can just kind of like do a little bit of arithmetic to figure out what we should be doing at this particular step. So at step 0, we just need to output the first word. At step 1, we need to start copying from group 2, and so on. And then we can count that, this group 2 contains only 2 words. And so with a little bit of arithmetic, we can figure out that at the third step, we need to move on to the next symbol in the reassembly rule and output, in this case, the word you. Sorry. And so that's kind of what we assume the model can do. And the next question is, suppose we know where in group 2, how do we identify the next token to copy at each particular input generation step? And so for this particular mechanism, we consider 2 kind of general options, or 2 ways to figure out what to copy next. The first option is we call content-based attention, so similar to the induction head mechanism. Here's another illustration where essentially at every generation step, suppose at this step we know, we've generated your boyfriend, say, and so we know that we need to keep on generating from group 2, and we could also use a kind of induction head style mechanism to say we know that the current word, that the last word that we generated is the word boyfriend. And so what we can do is we can look for a position in the input where the word is in the same group. So the word is in group 2, and the previous word was the word boyfriend. So in this case, the position where the word's in group 2 and the previous word was boyfriend is the word maid. And so if we have this information in the query and also the key, then we can implement this sort of simple copying mechanism to determine that the next word should also be made. So this is a ubiquitous mechanism in transformer language models, this kind of content-based or induction head-based copying. But there's also some kind of like possible failure cases. So one notable one is if the same prefix appears multiple times in the input, then it might not be so simple to distinguish which instance of the prefix to copy, because we're only copying based on content. So there will be like a collision if the same content appears more than once. And so kind of a second approach which circumvents this repetition problem is to keep on doing position arithmetic, basically. So similar to how we're calculating the state of the generation state at each step, we can also just do some more arithmetic to figure out the exact position to copy next. So, for example, if we know we've generated 2 words, your boyfriend, and we know the size of the different decomposition groups, we can do some addition to figure out that the next thing we need to do is we need to copy the second word of the group 2. And additionally, we can figure out what exact position that word appears at. And so just kind of copy by attending to the position embedding rather than the content. So this is a way of this mechanism works fine even if there's repeated tokens in the input, but some prior work has suggested that this kind of arbitrary position arithmetic might be harder to learn and might have show worse length generalization. But kind of a priori, these both seem like plausible mechanisms that a transformer could learn for handling this kind of like subtask of the ELIZA program. Okay. Now we'll move on to these long-term memory mechanisms. So the first memory mechanism is cycling through multiple response rules. So in this case, we have the same template that's matched more than once. And so the logic that Eliza needs to do is say, the second time I've matched this template, I should respond with the second response rule, and so on, eventually cycling back to the beginning of the list. So here also we consider two kind of general ways of like approaching this subtask with a transformer. The first one that this was the most obvious to me, I think, is just count up the number of times we've seen each template. So the idea is here in this illustration, we have uh, some sequence of user inputs, analyzer responses, and in these lower layers, we are comparing the input to all of our different templates, and we can determine kind of in parallel for each input, say this has matched template one. Then we can stack on top of that just a counting layer that will say how many times have I matched template one so far, and then output the count modulo the number of responses associated with this particular rule. So in this case, if we have only two rules, then we'll count one, response one, response two, and so on. And this is just kind of a very kind of like hand wavy guess. To me, is that this kind of mechanism, it's I think conceptually very simple, but it seems maybe more difficult for a transformer to actually learn. So you need to do kind of broad attention over the whole sequence. You need to do this modular counting, and you also need to learn a different modulus for each rule. So different rules can have more or fewer responses, and so you need to do something a little bit different for depending on the number of response rules. A second approach that avoids counting is that we can kind of reuse our template matching mechanism, but apply it to Eliza's intermediate outputs. So in particular, in the same way that every like input, for all the inputs we have different decomposition templates, we can also think of an equivalent process for just looking at Eliza's previous response and trying to figure out which response rule was Eliza using at every turn. So this is going to kind of take place in parallel to template matching for the inputs. And if we have this information available, so for example, say that at this point, we can see that the most, Eliza has previously used this response rule, I'm sorry to hear your blank. Then we can just look at the most recent turn where Eliza has responded to this particular decomposition template and just increment our cycle counter by one. So you can say if the last response is, I'm sorry to hear your blank, then the next response should be this response two. Can you explain what made you blank also? So this is kind of like, in a way, more reminiscent of sort of a chain of thought type of approach to simulating this particular data structure, the response cycle. So instead of having to actually count up the whole prefix so far, we can kind of make use of the fact that Eliza in the previous output has done some calculation that we can sort of reuse by attending to Eliza's previous outputs in addition to just the user inputs. The last mechanism is this memory queue. And so here we have this queue that contains any input that matches a particular prefix. And the logic we need to implement is if the current input is null, so if the input doesn't match any template, and the queue is not empty, we need to read the first memory from the queue. And I was supposed to have animations here, but if you just look at one thing at a time. Starting at the left, similar to for the previous slide, we can also think of two kind of like general approaches to kind of simulating this data structure. Um, the first on the left is essentially reusing kind of like a automaton construction from prior work as like a black box widget, basically. So um, the main idea is it's easy to using just the template matching mechanism. We can identify for every input is this a memory input, so it should be enqueued. It should be added to our memory queue, or if there's a null input that doesn't match any of our existing templates. And the tricky thing is, given a null input, we need to decide uh, how many memories are on the queue. Um, and yeah, at a high level, what makes it tricky is, um, you know, if you think about it, there's sort of like a, a, a chicken and egg kind of problem because at this particular layer, we don't know whether or not we should dequeue. So it's not clear whether or not um, we should read something from the queue. And so we have to calculate the state without, yet knowing like what we're going to do to the queue at this particular time step. And so the one way to do this is using this 1D grid world automaton from prior work. So um, here, a 1D grid world is if you imagine a one-dimensional grid with a maximum size S, there are two actions in the grid world, which is increment the state if possible and decrement the state if possible. And you can kind of translate this to the memory queue situation, where if we can just fix the size of the memory queue at S, every time we have an input that matches the enqueue action, so my boyfriend made me come here, or my father is afraid of everyone, we could treat that as increment the state if possible. So add it to the queue unless we're at the maximum queue size. And then the no match input, so if we have an input that matches the null template, or it doesn't match any template, then we could treat that as decrement the state if possible. So if there's any memories in the queue, then we're going to read that memory and then move the queue counter down by 1. So our queue size is decreasing by 1 step. And so then, every time we've decremented the state, then that should correspond to a dequeue action. So at this first input that doesn't match a template, the queue is empty, so we just respond with some generic null response. But then enqueue will increase the size of the queue by 1. So then the next null input will dequeue, and now the queue size goes back to size 0. And so the next no match input, once again, we have to just respond with our generic null response. So that's option 1, kind of using this like black box automaton. Then option 2 is similar to on the previous slide. We can also make use of the ELIZA's previous outputs to kind of like to save ourselves from having to implement this whole automaton. And so in particular, we can reuse our template matching mechanism applied to the ELIZA outputs to detect any output that corresponds to the dequeue template. So for example, we can see, at this step, ELIZA has said, does that have to do with the fact that your boyfriend made you come here? In this illustration, that corresponds to this box here, where we can see that at this previous step, ELIZA has given an answer that uses the dequeue response template, and so then at the next transformer layer, we can just count up and earlier in the sequence, how many times have we seen an enqueue input, and how many times have we seen a dequeue response? And this just directly gives the number of queues in the memory queue, or the number of memories in the memory queue at the current time step. And that's, again, in a sort of hand wavy way, maybe a little bit simpler than doing the whole grid world, because you just have to count the difference between the number of enqueues and the number of dequeues. Any questions so far? I see one question.
Yeah. Like when sampling conversations, uh, the queue contains at least most four memories at a time. Why is that?
Oh, that was okay. Yeah, so this maybe jumping ahead
Okay. Okay.
to our experiments. Yeah, so in our experiments, we just arbitrarily picked a maximum queue size of four. Um, there's not a real reason uh, other than to kind of like basically we wanted the data to contain um, to illustrate the different behaviors of the model. So we want to make sure that we'll have conversations where, for example, the queue will be, we'll have a bunch of memories in the queue, um, and then also cases where the queue had been used and then emptied out, so that we have to go back to this situation where the um, the queue was non-empty earlier in the conversation, but it's empty now. Um,
Mhm.
yeah.
So does the data structure also has some kind of a memory limitation here, or like some compute issues? Why you are choosing four? So I was just wondering, maybe you can have six or 10.
Yeah, we could have. Um, yeah, there's no real reason. I mean, there's no real reason in the data set. It's just more to do with the fact like four was just in a way an arbitrary choice based partly
Okay.
on like the average like length because we do fix the context size to like I don't know
Mm-hmm.
500 or something, and so based on just the total number of uh, or the average number of conversation turns, you'll have in that limited context size. Having an overly big memory queue would be kind of uh, or at a certain point there wouldn't be like it would never really use able to make use of like a infinitely big memory queue.
Mm-hmm. Yeah, got it. Thanks.
Um, yeah, that's so maybe a good segue to the experiment section. So to recap, we've kind of like gone through these different subtasks of ELIZA and kind of like tried to think about like different ways that a transformer could carry out these different subtasks. And in some cases, identifying kind of like two uh, broad options. Um, yeah, and so in this next part of the talk, I'll just describe some of our experiments. So basically, our approach is we generated synthetic ELIZA conversations and then trained the transformers to simulate the ELIZA algorithm. So to generate the correct response at each step. Um, and some of our general questions are one kind of like just from a sort of a qualitative point of view, what aspects of the task seem easier or maybe more difficult for the model to learn. Uh, and also, which of our constructions seems to be a better match for what the models learn, especially in these cases where we have more than one possible or more than one hypothesis. Um, and so our data, this is all just synthetic data using 26 word vocabulary. And our general approach is we sample a script. So this is an inventory of decomposition templates and reassembly rules. So here's an example of a decomposition template and an associated reassembly rule. Um, and we also set it up so that every reassembly rule will begin with a unique two-letter prefix. So this will give us a proxy for measuring, um, for distinguishing between one, did the model identify the correct rule? And then two, did the model carry out that reassembly rule correctly? So the idea is if the model gets the correct prefix, then we think, okay, it maybe has identified the rule, even if it doesn't do all the copying right. Then for each, to generate conversation data, we take each one of these decomposition templates and sample a sentence that matches the template. So for each wildcard in the template, we sample just some number of, some sequence of characters uniformly from the vocabulary. and then apply the corresponding reassembly rule. Here's just our first, some kind of basic training results. We, throughout the experiments, just fixed the size of the transformer to just 8 layers. And there's many possible configuration choices for the data, but we just fix it to the parameters described here. Here we have the training accuracy over the course of training, and then in this figure on the right, just some breakdown of the accuracy and these different turn types at the end of training. The main thing to observe is just that the models learn to simulate ELIZA quite well. So the accuracy on all categories goes up to almost 100% by the end of training. This is maybe hard to see, but perhaps not surprisingly, the prefix only accuracy converges quicker than the full response accuracy. So the models are very quick at learning to identify the correct rule, and they take maybe a little bit longer to learn how to implement the reconstruction rule correctly. So to do all the copying and stuff. So here on the right, we zoom way in to see if there's any differences on the accuracy based on these different turn categories. So the way we can divide the data according to turn is as follows. So single turn is just the first turn in the conversation. So for the first turn in the conversation, the model doesn't have to do any cycling. It doesn't have to do any input segmentation or anything like that. Then the multi-turn category is it's some turn from later in the conversation, but the first turn where a particular decomposition template has appeared. So this is the first time you see template T, so before you have to do any kind of cycling. Then the green bar is the a later turn where you have to you've matched the same template more than once, and so the model needs to do some kind of cycling. And then we have memory queue turns and null template turns. So the null template is a case where we have an input that doesn't match any decomposition templates, and also the memory queue is empty. And so it's a little bit surprising that the null template is one of the worst categories. But it's maybe not surprising that the memory queue in general is maybe a little harder for the model to learn, because this kind of involves in a way a composition of all of these subtasks. So for this memory queue behavior, the model still has to do the local pattern matching, and then it has to also calculate the state of the memory queue. And then on top of that, the memory queue can also have multiple memory responses associated with it. And so the model still has to do some cycling as well to do this memory queue thing successfully. We did a little bit of kind of qualitative error analysis. So to look at these kind of sort of individual errors, and we noticed two general kinds of errors. So the first is copying errors. So here we are plotting the errors as a function of two things. One is the number of copying segments in the reassembly rule. So that's the color, 1, 2, or 3. I'm sorry, going back. Yeah, to give an example, in this reassembly rule, this has 2 copying segments. So there's 2 distinct places in the reassembly rule where the model has to copy a different segment of the user's input. And so you could think of the number of copying segments as maybe a proxy for the complexity of this reassembly rule. But then on the x-axis, we have just the total number of tokens that the model has to copy in this particular example. And you can see that the error goes, the model's error rate is correlated with the number of tokens. It's maybe a little bit correlated with the number of copying segments. So it's a little bit worse when there's 3 copying segments and 2 copying segments compared to 1. But there's an even bigger drop off when you just have more tokens to copy. So that's maybe a hint that the model maybe struggles a little bit with this sort of precise copying as the segments get longer. But then there's also some correlations with different properties of the memory queue. So here we won't go into great detail for lack of time, but the general observation is that when we've done more queue operations, so if there have been more total like NQs or DQs, then the error rate on that these memory queue categories goes up accordingly. So this is all just some sort of qualitative error analysis. And in the next section, we wanted to do a little bit of an investigation of what kind of mechanisms does the model seem to learn for these cases where we had kind of two plausible hypotheses. So the first is for copying. So we had, again, 2 hypotheses about copying mechanisms. One is the sort of content-based attention based on the induction head, which could fail if the n-grams aren't unique. And then the second is position-based attention based on kind of calculating the exact position to attend to, which might be harder to learn. And so we have some preliminary evidence that the models are using content-based attention just from the fact that the error rate is going up when there's more tokens to copy. And here's an additional breakdown where we plot the error rate as a function of the proportion of n-grams in the sequence that are unique for n equals 1, 2, or 3. And you can see that when there's more repeated n-grams, so going from right to left, the error rate, the accuracy goes down. And there's a bigger drop when the non-unique n-grams are longer. So if we have like a bunch of repeated 3 grams, then you see a pretty big drop in accuracy. And so we did a little bit more investigation of what mechanisms these models actually learn, and also how does this depend on the data distribution. So in particular, we trained an additional set of models on data where we varied how likely it is for a copying segment to contain the same n-gram multiple times. And I won't go into great detail, but basically we can control the distribution of words that we sample for each wildcard segment based on this Dirichlet distribution, which has a concentration parameter. And so the idea is if we set this concentration parameter to be low, so like less than 1, then it's more likely for the corresponding input segment to contain the same words multiple times. And if we set alpha to a high value, so greater than 1, then our distribution will be like a uniform distribution over a vocabulary. And as a result, it's becomes less likely for the same n-gram to appear multiple times in the same sequence. So we created 4 data sets like this and trained models and evaluated them on the different data with different amounts of repetition. And here in these plots, you have the training accuracy. So each column corresponds to the training distribution, and each color corresponds to the evaluation distribution. And what you can see is when there's more repetition, so for example, the concentration is equal to 100, the models do well on sort of in distribution. So when you have similarly like non-repetitive data, but there's a big drop off on these colored lines where there's, when the data becomes more repetitive, these models do a lot worse, which maybe would be consistent with the expectation of these. When there's not a lot of repetition in the data, the models will maybe learn this sort of induction head style mechanism, and as a result, generalize worse when we have if we introduce more repetition into the data. On the other hand, these models with like a lower trained on like more repetitive data, they generalize a little bit better to less repetitive data, and yeah, they also work on data where there's a lot of repetition. Then so that's just sort of the kind of behavioral evidence. We also did a just sort of very basic like kind of probing type of experiment to see, looking at the attention heads, do these attention heads attend more to positions with the matching content or to positions with like the matching position, correspond to these two different mechanisms. I'm running out of, I don't have a lot of time left, so I'll just say, to maybe summarize this result, when we train models on data that has relatively low rates of n-gram repetition, the models almost always are attending to content rather than score. So on this plot, a positive value means that the model assigns higher attention scores to positions with the correct content relative to positions with the correct position. And so you can see in all cases, like the models are giving higher content scores as the n-gram length goes up. So the models will assign a higher score to positions with the matching 4 gram compared to positions with the matching 3 gram and 2 gram and 1 gram and so on. But it's only with these models on the left where they've been trained on more repetitive data that they'll assign relatively higher attention scores to positions with the matching position rather than positions with the matching content. So this is maybe some evidence that like we can sort of influence the model to learn this position-based mechanism by adjusting the data distribution. Briefly, we also did some investigation into these two long-term memory mechanisms, where we had one hypothesis based on simulating an automaton, where this is applied only to the user's inputs and doesn't take advantage of ELIZA's intermediate responses. And then we have a second memory mechanism that can take advantage of the intermediate ELIZA responses. And so we just did like a basic test to see to what extent do the models use their intermediate outputs, where we created a counterfactual data set by taking an example that demonstrates the corresponding memory mechanism. So in this case, the cycling through responses, and then editing the a previous response to kind of like try to create this counterfactual scenario. So in this case, we can take this previous response and generate this alternative response where we've like adjusted the cycle number. So we make ELIZA respond to this previous input as if the template has been matched one more time than it actually was in the conversation. This gives rise to the prediction where if the model's just counting the number of times a template has been matched, its response should stay the same. So it should ignore its previous responses and still output the response that it would output just based on a count of the number of times a template has been matched. But if the model is just using its previous outputs to figure out the cycle number, then we predict that the model will increment its response according to like the amount we've incremented the cycling number. And so here we just plot the proportion of responses where the model's new behavior is either the same as it was before, it's incremented according to our prediction, or it's something else that we don't understand. It's it doesn't match either prediction. And so here we have the full response accuracy and the prefix only accuracy. And you can see, especially in terms of prefix only accuracy, most of the time the model is incrementing its cycle number in a way that's consistent with this intermediate output hypothesis. And we did a similar experiment for the memory queue where we can change a previous response and make a prediction about whether the response will stay the same or whether it will change in a way that's predicted by our hypothesis. And in both cases, the model behavior is more consistent with this idea that the model is really making use of its prior intermediate outputs to simulate this recurrent data structure. So that's about my time. So I'll just put my conclusions here on the last slide. Yeah, I can take questions if there's any questions.
You can still go for your conclusions if you want to. We have time.
Okay. Yeah, all right. Well, so to summarize, we've constructed a transformer that implements this ELIZA algorithm. And on one hand, we can kind of make use of like these maybe simpler constructions as like essentially black box components or widgets to give rise to this kind of more complex conversational behavior. But I think the construction also highlights cases where there's really more than one way that you can solve any particular task with a transformer. And it's kind of interesting to figure out like which constructions are a better match for what transformers are maybe more likely to learn in practice when you just train them on some data. And I think in general, this ELIZA setting offers an interesting test bed for these kinds of analyses and questions because we have a case where we have kind of an interesting compositional task and we can connect it to kind of specific hypotheses about what the model will learn and how this will affect the predictions. And I think there's a number of other possible questions or next steps, like one is to think of ELIZA as kind of a benchmark for interpretability. So even just as a thought experiment, you can kind of wonder to what extent could mechanistic interpretability tools recover the ELIZA algorithm if we knew that the transformer was, say, encoding it like our constructing. I think that's sort of interesting food for thought. And I also just think there's a lot more kind of questions about kind of learning dynamics and learning mechanisms that exceeded the scope of our paper, but could be interesting to discuss. So we have the code and data is available on GitHub. I didn't include the paper link here, but it's on archive. And you can feel free to email me if you have any questions. I see.